This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
The second part of this chapter deals with what's known as discounting and net present values. Now, the concept behind discounting and present values or net present values is something which is called time value of money. And the idea behind the time value of money is that money, even though it looks to be the same amount, money received earlier is worth more than money received later. So if we look at these examples here, let's say that the interest rate is 6%. One way we can see the advantage of receiving the money earlier is if we compare these three same amounts, $1,000, being received now on 1 year or in 3 years' time. Dealing with the first two here, well, what you can say is, if I receive the money now, I can put it aside in the bank, and in 1 year's time, I would have 1060 in the bank. And of course, this is clearly better than having to wait a year before you get your 1,000 coming in. And if we were to say, well, let's compare it to what we'll get in 3 years, well, if I receive an amount of 1,000 now, and if you remember how to do the compounding, in 3 years' time, it's going to be 1,000 times 1.06 raised to the power of 3. It's going to be, I think, 1191. And what we really do is saying, well, if you wait for 3 years before you get your 1,000, you'd only have 1,000 then. But if you've got the money now and put it aside for 3 years, then you'd have 1191. And it's clearly much, much better now to have the money earlier than later. Now, those examples use the idea of compounding, in other words, kind of taking forward, to see the amounts of money that you'd end up with. What discounting does, it brings back to the present value. It says if we had received that amount of money, or rather it says how much money would we need to receive now to be the same as receiving an amount, let's say 1,000 in 1 year. So if 1,000 received now, that is already the present value. Okay, 1,000 received now is exactly like 1,000 received now. But what we're really saying for this 1,000 here received in a year's time, we're saying how much would we need to receive today, so we could put it aside at 6% so that it would become 1,000 in a year. So if we receive X now, we can put that on deposit at 6% for 1 year, and that is to become 1,000. In other words, it mimics or is exactly the same worth as receiving 1,000 in 1 year. So the X in here is equal to 1,000 over 1.06, or it's 1,000 times 1 divided by 1.06. It's 943 equals 943. Or if we didn't receive the money until 3 years' time, we're saying how much would we need to receive now? We put it aside on deposit for 3 years so that it becomes 1,000 in 3 years' time. It completely mimics getting 1,000 in 3 years' time. Then we can see here X is going to be 1,000. I'll write this one slightly different. times 1 over 1.06 cubed. It's really say we're dividing through by 1.06 cubed. That's 1,000 times, so if I take 1.06, 1 divided by 1.06 is equal to that. If I raise it to the power 3, we're going to be equal to 0.840. Equal to 840. So clearly it is better receiving 1,000 now than the equivalent of receiving 943 now, which in turn is better than the equivalent of having to wait 3 years, and that's equivalent to receiving 840 now. So what discounting does, it reduces all future flows, their present values, by discounting, and these amounts here, these are known as discount factors. And the general formula for a discount factor is 1 over 1 plus r to the n. Where to bring it back to the present, you put in the interest rate again as a decimal, and you put in a number of years. So in here we've put in 6% as a decimal, and we've put in a number of years in there, and this allows us to reduce that. What looks like 1,000 coming in 3 years is AR, but it's really only the same as getting 840 now. Now this business of working out these discount factors, if you're having to do it for a lot, can become a little bit tedious. And what's available, and will be available in the exam, is what's called discount tables, and they do the work for you. So if you just check this for 6%, say for 1 year here, the discount tables would look like this. They have the rates going along the topic with the number of years going down the side here. So here's our 6% column, and here's our 1 year row, and you see in here 0.943. And if we go to the 3 year one down here, there we have 0.84 in there, 3 years at 6%. So this very easily allows us to work out, by using these tables, what the present values of amounts are. So let's see a little example. Is it better to, let's say, receive 2,000 in, let's say, 4 years, or is it better to receive, let's say, 2,700 in 6 years? And we'll say the discount rate or the interest rate we're going to be applying in here, let's call it 4%. So this is difficult to look at and say maybe which is better here, because the amounts are different and the years are different, and the only valid way to compare them is to reduce both amounts to their present value. So we take the 2,000 here, we're dealing with 4%, so in this column here, and we're saying it was received in 4 years, so the 4 year column there, 0.855. So we're saying the present value of receiving 2,000 in 4 years, the present value is 2,000 times 0.855 is 1710. Quite a big reduction there. Yeah, if you think about it, 4% is a very modest rate. 4 years isn't very long away, but already we've lost 15% really of the face value of the money. The 2,700, which has been received in 6 years and 4%, we go down here, and that's the amount there, 0.79. So 2,700 times 0.79, 2138. And we see quite clearly here that the preferable receipt that we're going to be having is to receive the 2,700 in 6 years. So the rule for all present value calculations really is to reduce all cash flows to their present value. What would they be equivalent to if the flows were happening now? Now, quite often what you will find in present value problems is you have what's called an annuity. An annuity is a constant amount, annual amount. For a number of years. To make it easy, there is an example, and then we'll see an easy way of doing it with some more tables. So let's say we have 1,000 received at times 1, 2, 3, and 4. This could be rent on a property that you or lease income coming in and something you're leasing to somebody, constant amount for the 4 years. The discount rate is 8%. Now the long way round of doing this is to say, well, I'm getting the first money at time 1 in a year's time, so I can go to my 1,000, this is my time 1 flow, and I'm going to multiply that by the 8% factor for time 1. So the 8% factor at time 1 is 0.926. And then times 2 and times 3 and times 4 have 1,000 and 1,000 and 1,000. And we'll get to 3 discount factors for that. Rather than going backwards and forwards, I'll just work out what they are really. So we had 1 divided by 1.08. So you can either do it by calculation, which is basically the calculation 1 over 1 plus r to the n, or do it through the tables. So here it's slightly easier doing the tables rather than flipping backwards and forwards. So that is 0.926 and divided by 1.08. The next one here is going to be 0.857 divided by 1.08. The next factor is going to be 0.794 and divided by 1.08 again is going to be 0.735. So these flows of money, 1,000 a year for 4 years, the present value is going to be 926, 857, 794 and 735. So we add all of that up, 926 plus 857 plus 794 plus 735, 3312. A long way short of just saying 1,000 being received for 4 years is worth 4,000, because 4 years away, you're having to wait quite a long time for your money. It's not worth nearly as much as the face value is down to that 73.5% of its face value. Now that's really rather tedious to do that. We've had 4 multiplications in there. We've had 4 discount factors either to calculate or to work out. Another way we could have done it is to say, well, maybe it's 1,000 times presumably 3.312 in there. So 1,000 times 3.312, this is what these are going to be adding up to in here, is going to give us the present value of 4 flows. Now, because it's very common to have annuities, as I say, things like leases, things like rents, constant annual amounts for a number of years, it's made easy for you. Rather than having to work out 4 discount factors or find them and add them up and so on, there are tables called annuity tables. So here, this is a cumulative present value, receivable payable at the end of each year for n years. So we were dealing with 8%, and we were dealing with 4 years. I don't know if you can see it in there, but I'd say it's 3.312. So the way we could set out this calculation, instead of setting it out all longhand like that, we could simply say, right, years 1 to 4, we're receiving 1,000. The cumulative discount factor from the tables is 3.312, and therefore the present value is going to be 3312. So these cumulative tables give you a fantastic kind of shortcut to working out the present value of annuities. Note, however, they all start with year 1. They are the cumulative factor for year 1 up to whatever year you're going to go to. And if you don't have a perfect annuity starting in year 1, then you just have to be a little bit cautious. So let's say we had a slightly unusual set of flows. Let's say that we're going to be receiving, let's call it $5,000, and let's say the discount rate is, let's say, 6%, and we're going to be receiving this 4 times 4 to 10. So we're not going to be receiving anything in times 1, 2, and 3, but then we're going to be receiving 4, 5, 6, 7, 8, 9, 10. We're going to be receiving 7 amounts, because it's 4 to 10 inclusive. We're going to be receiving 7 flows of 5,000. Now the way to do this is to say, well, if I go to my 6% here, and I can go to my 10 years here, and we have 7.36. So the cumulative factor for 1 to 10 is 7.36. And the factor for 1 to 3, that one there, 2.673. 0 in there. And as you subtract one from the other, you are left with 4 to 10. So we're going to have in here 7, 8, 6, and 4. Let me just check that subtraction. Here, 7.36 minus 2.673. Yep, 4.687. So the present value of this amount here is 5,000 times 4.687. Is going to be 23,435. So we can construct these irregular annuities, if you want to call them that, from the annuity tables, and you still save a lot of work. Where people go wrong in this is they don't take off 1 to 3. They will see it's 4 to 10. They take off 1 to 4. But that will only leave them then 5 to 10. Okay, you have to remove the 3 years at the start you don't want to leave you with the 7 years at the end that you still do want. So, how is discounting used in what's called project appraisal? And what's known as capital projects usually means you buy a piece of machinery now, and then you get income from it maybe the next 5 or 10 years. And because of this big time differences between spending the money now and getting the income coming in the future, it is essential to discount the flows, or to use discounted cash flows. So here's a typical little simple project. We want to work out, is it a worthwhile project? Using something called the present value, or the net present value. So you simply set out the flows to start with. So a project costs 10,000, and usually that's going to be now. And now is shown by time 0 now, and it's a flow going out, so it'll normally be put in brackets, and the discount factor is 1 because it's going out now, it's already in present value terms, so discounted cash flow is simply 10,000 going out. Then at time 1 we receive 3,000. At times 2 we're going to be receiving 8,000, and at time 3 we're going to be receiving 5,000. Now these are flows in the future, and to use them validly we have to bring them back to their present value, and we're using, again, if I turn to it, we're using 10% discount tables, but it's going to be easier if I just kind of work it out on my calculator, because again it's 1 over 1.1, the 10%, to whatever number of years we want there. So 1 divided by 1.1 in there, 0.909. The next one, 0.826. And the next one, 0.751. So our discounted cash flows would be 3,000 times 0.909. It's something wrong there, 2727. At time 2 we get 8,000, but because it's 2 years away it has to be discounted by the factor of 0.826, 6608. And the next one, 5,000 times 0.751, 3755. And these are all positive because they're inflows. And all we do is we add them up. So we have 3755 plus 6608 plus 2727 minus 10,000, and it's 3090. And this is called the net present value. Or NPV. It simply is the net of the present values of the inflows or the outflows. So it's 3090. So the rule is if the net present value is greater than 0, you've made money. The present value of the inflows exceeds the present value of the outflows, and you would accept the project. If it's less than 0, that means the present value of the outflows is greater than the present values of the inflows. You're losing money, and you can avoid that by simply rejecting the project. So net present value is absolutely the most common, the most intellectually responsible way respectable way of appraising projects. Take into account the time value of money, because quite frankly, if you get an amount of 10,000, and let's say it's in 10 years' time, and you're using a discount rate, let's say, of 10%, so we have 1 over 1.1, raise that to the power of 10, we have there the discount rate is 0.3855, then that 10,000 is really worth 3855. It's worth, it's well less than half of what the face value of that is. And it's all very well so we're going to get all this money in the future, but you're having to wait an awful long time for it, but you're spending the money now. So the time differences, the elapse of time, has to be taken into account. This, again, is where annuities can become extremely efficient. So here we have one other example. Project costs 10,000, so we can say at time naught we have 10,000 going out. Discount factor is 1 because it's happening now 10,000. And then rather than write out 5 lines, each with the 3,000 coming in, we say, right, it's 1 to 5, and it's 5,000 coming in. And what we want is a 5-year 10% cumulative discount factor. So what I'll do is I'll go back and have a look at what the 5-year 10% cumulative discount factor would have said. So here we have 10%, and we want 5 years, since 5 years is going to be there, 3.791. So 3.791. So 5,000 times 3.791 is 18,955. So the net present value we're going to be having in there is 8,955. It is greater than 0, therefore accept this project too. So if you see annuities, do try to remember and be able to use annuity tables, annuity factors, because it's a great labour saving. And if there was a multiple choice type question coming up and you didn't use annuity factors when you could use annuity factors, you're going to spend an awfully long time doing the workings for that question. And because there are lots and lots of workings in writing this all out, kind of years 1 to 5 and so on, more workings means, of course, more chances of going wrong. So it's a really good skill to master these cumulative discount tables. An alternative approach is, let's just say return. An alternative approach is to work out the internal rate of return, or the IRR, of a project. And the internal rate of return is defined as the discount rate at which the net present value is 0, a kind of break-even discount rate. So here we have a little project. This would be regarded as a conventional project where you spend the money now and then you get money in the future. Now, if you're spending money now, that money spent today is not affected by the discount rate. The discount factor is always going to be 1. But as you raise the discount rate, what you're doing is you're eating into the value of flows in the future. So if we have in here, at a very low discount rate, here we put in here 5% as a discount rate, there's a good chance the project will be positive there, because we're not discounting the future inflows very much. But if we were to hike the discount rate up, maybe, as I've suggested in here, to 15%, 15% is really eating into those future positive inflows a lot, although the negative outflow times 0 has not been affected. So what we're doing is we're gradually increasing the chance that the project is going to go from a positive NPV, here's our net present value, down to a negative NPV. And in here we have the internal rate of return, or estimated internal rate of return. If it's positive at 5% and a negative NPV at 15%, then presumably we've travelled through 0 NPV, somewhere in between 5 and 15%, and we'd have found the internal rate of return. The rule is that if all the way to the left here, the actual discount rate is less than the internal rate of return, then you have a positive NPV. So the discount rate is less than the internal rate of return, then you're going to have what's called a positive NPV. If the discount rate is greater than the internal rate of return, which is all the way down here, then you're going to be a negative NPV. This is a little bit saying I'm borrowing money from the bank maybe at 12%, and I'm putting it into a project which is maybe only earning me 9%. And that doesn't make sense. Borrowing at 12%, putting into something that's earning 9%, you're obviously going to lose out. And you can avoid losing out by, of course, simply rejecting that one and accepting that one. So we know the internal rate of return, we know the discount rate, then we can use that as, again, another accept or reject kind of criteria, just as well as we can use net present value. But it's slightly more work, but we have to know how to do it. So let's say this is what it is. What you have to do is to work out two different net present values at two different discount rates. I've chosen here 5% and 15%. There's no reason why you couldn't maybe choose 3% and 17% or 6% and 13% and so on. That's quite arbitrary. It's nice if you get one positive NPV coming out and one negative NPV coming out. Here I have a plus 1,000, this is minus 1,300, because we know then that the internal rate of return is somewhere in between the 5 and the 15%, but it's not essential. And then you can either use a little bit of geometry, or then we'll see a formula which you might prefer to use. What we have here is basically we've got something called similar triangles. In other words, we've got the same proportions. So ABF, the triangle ABF here, which is this little one up here, and this big one down here, ACD, what's called similar. In other words, their sides have got the same proportions, just kind of a scaled up version of each other. What we really want to find out here is BF. So we know that this is 5. If we found BF, then we would know how much above 5% the internal rate of return actually is. So if I take the base over the height, so if I took BF over AB in the small triangle, this is going to be the same as in the big triangle, which is CD, the base over the height, over AC. So base over height in both triangles, because they're just proportional, just scaled up, scaled down versions of one another, is going to be the same. So we want BF. We want how far above the 5% our first arbitrary discount rate that the internal rate of return is. So the BF there is going to be AB times CD over AC. So reading the figures off here, AB is 1,000. CD is this distance here, 15 minus 5. And the bottom here, A to C, that's 1,000. And this distance here, I put in as 1,300. So what we've got basically in here is 1,000 more 10,000 on the top line, 1,000 times 10 over 2,300 on the bottom line. .34. Let's go 4.3. So this is BF. This distance in here is 4.3. So therefore the internal rate of return is going to be 5 plus this distance is going to be 9.43. And you see here, I put a kind of 10 in there. It's drawn roughly to scale, is this diagram. And you see it looks as though it's getting quite close to the 10, slightly lower than 10. I would believe around 9, 9.5, something of that sort, is going to be the internal rate of return. Now, if you don't want to draw these little diagrams and do it by similar triangles, then you have to learn a formula. And the formula is the internal rate of return is equal to A%, and I'll say what all of these are in a moment, plus NA over NA minus NB, B minus A%. Where A equals a lower discount rate. In other words, it's going to be 5. B equals a higher discount rate. So B in here is going to be, we've tried it at 15. Minus A minus 5. So we're getting, you see, the same in here. We've had to add on, a plus 5 in there. Yeah. So it's 5 plus whatever this extra distance is. NA is the discount rate, is the present value at A%. So NA equals present value at A%. So that is 1,000. You see this formula coming out in here, 1,000, 15 minus 5. And where you need to be careful, because NB equals the present value at B%, NA is 1,000, but it's minus, here, minus 1,300. And a minus is a plus. So we had in here, basically, 2,300. So it's going to come out to be exactly the same as before. Just watch the algebra. You want one of these to be positive. You want one of the net present values to be negative. And this bottom line here, NA minus NB, if you get that, you have to do NA minus NB, but NB is itself minus a negative figure. So it ends up essentially adding the two net present values together.